So there are many different functional forms that you might see, but we want to focus on two more that you'll probably certainly see in supply chain management. That is the power function and exponential functions. So let me just take a minute to talk about those. So first, the power function. It takes the form y equals a times x raised to the b, where a and b again are constants. So the shape of this curve is really dictated by that value b. And so what I'm going to show you here are different curves based on different values of that b, the power that you're raising the variable to. So on this chart, the horizontal axis is the x and the vertical axis is the y. And here's a chart for where a equals 1 and b equals 1. So notice that if b equals 1, it's a linear function. So it's going to increase every a units for every 1 unit in the x, right? It's just turning into the slope. The only thing it's missing is an added constant or a y-intercept. So it assumes the y-intercept here is 0. So if b is equal to 1, then it's pretty straightforward. It's a linear equation. Typically, though, you'll see b greater than 1. And this is where that function will increase exponentially. It'll keep increasing faster and faster. And so you'll see something like a times x squared or cubed. And so in this case, the value increases dramatically. Sometimes you'll see it where the b is between 0 and 1. What does this mean? It's similar to what we showed in the example for parcel shipping as a function of weight, where it goes below the linear, right? Especially when you go beyond the value of x equals 1, it tapers off of that. And then one case that I want you to look at is what happens if b is less than 0. So if b is negative, then this means this function will decrease asymptotically to 0. Asymptotically simply means it approaches but never reaches. So this function will always get, this purple one that goes from the top left all the way down, will keep getting closer and closer and closer to 0, but will never ever reach it. Now, why is this important? Well, if you have a b, let's say it's equal to -1, so your function is y equals a times x to the -1, that's the same thing as saying that y is equal to a divided by x. Remember, a negative exponential is simply putting it in the denominator. So you'll see this a lot if you are allocating a fixed cost. So let's say I have a truck and it costs $1,000 for a truckload to go from some point to another point. And it holds up to 20 pallets. If I only have one pallet on there, then that $1,000 cost is divided by one pallet, and so that pallet will have to absorb all $1,000 of that cost. However, if I have two pallets, suddenly that 1,000 now is divided by 2, so each of the pallets absorbs 500. If I have 10 pallets on there, it's 1,000 divided by 10, each one absorbs 100. So you see what's happening here, it's following this power function, it's going down. So you'll see this a lot when we look at allocating costs. You'll see it when we look at inventory, when we're trying to figure out the effect of having a larger order size. So we'll do this very frequently. So the power function will be widely, there we go, let me go back, will be widely used. And we'll see it in inventory. We'll see it when we look at the propensity of disruptions. You'll see it in segmentation. Okay, so now let's go to the exponential function, which is very similar. And the exponential function is simply y equals a times b, where b is raised to the x. And remember, a and b are constant. The variable is x. So what does this look like? Here's my chart. X-axis on the horizontal, y-axis is on the vertical. And here's an example where a equals 1 and b equals 2. So 2 to the x. So as the x value increases from 1, right, to 2, to 3, to 4, you see it's increasingly at an increasing rate. It increases at an exponential rate, thus the name of the function. And so if y equals 3 to the x, this is where a equals 1 and b equals 3. As you increase from x equals 1 to 2 to 3 to 4, it increases at an even faster rate. This is where the term exponential growth comes from. This exponential function is widely used, and it captures systems that have very fast growth. You see it in physics, biology, economics, finance, computer science, all over the place. In fact, you probably touch it every day. If you have money in the bank, you're taking advantage and utilizing an exponential function. and this is for calculating compound interest. So here I have the equation where the future cost, the future value rather, is equal to the principal value, how much I put in, times 1 plus the interest rate, and that is raised to the number of periods. So this is an exponential function. So for example, if I put $100 in and it has a 20% interest rate, then I'm going to multiply 100 times 1 plus 0.2, or 1.2, raised to the power of 5 if I keep it there for 5 years. So at the end of 5 years, that $100 will be valued at $248.80. So you're using this exponential function to capture the effect of compounded growth. Now, another piece that you'll see sometimes, you'll see the letter E sometimes. Now, what does this mean? This is just a special number in mathematics. It's called Euler's number, and it's used in what's known as the natural log. Let me talk about it really briefly, but you should just be comfortable with seeing it. It can go into a lot of depth. It's a really interesting mathematical concept that we won't spend too much time on, but I want you to not be freaked out if you see it. So essentially, E, or Euler's number, is a constant. Just like pi, it's the same kind of thing, and it's 2.71828. They find it by looking back at that interest rate example. Suppose that my interest rate is actually 100%. In other words, for every time period, I double. Now, this is something that actually does happen in some physics and some biology cases. That's why this is called the natural log. So let's say it doubles. And instead of checking it every year, I decide to check it every month, or every week, or every day, or every minute, right? As I decrease the time interval or increase the number of times that I check, then what happens is we approach a limit, and that limit becomes 2.718. In other words, that becomes the multiplier of that effect as I increase the number of n's, the number of periods that I'm checking. Now, if that explanation confused you, don't worry. Just take it as a fact. If I see the letter E, it means 2.718, and I'll explain in a later lecture why we use that. So I just wanted to make sure you understand and have seen these two other functions that you will see, a power function and exponential functions.